All right, here's a nice picture of Hess in his Navy uniform. So remember, this was in the 1960s. I'm sorry, in the 19. Well, it might have been in the 1960s, but he was actually in World War II. Um, but he continued to map the ocean floor, and found that there was this thing called ocean spreading, which led gave credence to these ideas that Wegener had about continental drift. Although we don't really refer to it as continental drift anymore. All right, so let's go back to, whoops, wrong thing. Here we go. So we were right here. All right. So this is so as these ridges, and we could just concentrate on the mid Atlantic ridge, but any of the ridges do this. So as new basalt and mixed with other things, in particular, if there's magnetite, which of course is a mineral, excuse me, that aligns with the Earth's magnetic field. As this stuff cools, it'll align with the current magnetic field, and like in other words, so let's say you're far from the ridge. So this blue line right here, or even go all the way to the green line right here. So this is a lot. This is much further back in time. This green line will all the magnetite that's in this green line will align with whatever the magnetic field was, during the time when those rocks solidified. All right, and of course this is the important thing. On the other side of the ridge, equally distant from the ridge, you have this other green line, and those the magnetite in those in that distance from the ridge is oriented exactly what the magnetite would be on the other side, right? So it's showing you basically what the magnetic field was doing, hundreds of thousands of years into geological past, and then like where the blue line is, there was a reversal where the the magnetic field, the poles switched. North was south and south was north. And I'm talking about the magnetic fields of the Earth. The magnetic field of the Earth switched, and that this goes on periodically every few 100,000 years. It switches, and we have this evidence that's locked into the rocks, deep within the ocean, and yeah, I mean this again. This was an important observation. We also got from this the rate at which the seafloor was spreading, right? Especially in the mid Atlantic, So from that, you can measure the distance from the western coast of Africa and the easternmost coast of South America, for example, and the distance between the 2 points, let's say at the same latitude or so, and then you can say, well, how fast is this spreading taking place, right? And so that's another measurement that we can make. All right, so I mean this idea of seafloor spreading and the magnetic reversal has given us tremendous information about the Earth and the very distant past. Okay, so hundreds of thousands to millions of years into the past. Let's see. So plate tectonics, this idea that the hot Earth causes the lithosphere to, remember, right below the lithosphere is the upper part of the mantle that's more or less like a plastic. It can kind of flow. It doesn't flow like really fast or anything like that, but it can flow. Um, and that the lithosphere lithosphere rides on top of it. And now the thing about the lithosphere is, it's very rigid, and it has cracked over time, right? It's broken into roughly 8 really large plates, and there's some smaller ones as well, right? And so these 8 large plates, this is the idea of plate tectonics, right? The lithosphere, these plates move around and they crash into each other, and that's how the continents move. All right, so that's we're going to dive into this. Um, all right, so this idea of plate tectonics, it's an underlining theory of geology, if you will, right? So everything is built on this idea that really came from our study of the seafloor spreading, right? So when we determined that the seafloor was changing, we figure out that of course this is because the Earth is a dynamic, active world, right? Because there's enough heat inside of the planet to drive those changes. Deep inside the planet compared to the surface of the planet. Other planets are different. For example, you get to you get to something like Mars. Mars is not considered an active world. I mean, it has a little bit of activity. In fact, we've landed seismometers on the surface of Mars and measured little Mars quakes, but they're really tiny. They're not like the way Earth is. There's not enough of a temperature difference to cause Mars to have these gigantic movements the way that's going on Earth, or even on Venus, for example. It's moving around. All right, so plates are sections of the Earth, these strong outer layers of the lithosphere, and so as I said, there's roughly 8 large ones. They're the uppermost part of the mantle and the crust. The plates ride on top of the upper mantle, which is also known as the asthenosphere, right? The asthenosphere. All right. All right. So here are the plates, or they're showing you. These are the color coded ones. This is, for example, this is the Nazca plate, the North American plate. Excuse me. The African plate. Although, by the way, the African plate, there's, although they're not really showing it right here, there's a possible. Remember, the Atlantic Ocean was just this small crack in the Earth a long time ago, during the time of Pangea, 250 million years ago. And so, South America and Africa were right next to each other. They were actually part of the same landmass. And that, we think, is actually happening right now. The African plate, there's a small region here, right about where I'm pointing, called the Somalian plate, or what might become the Somalian plate. And we think that, over geological time, so, millions of years into the future, that part will move away from Africa, and have it be its own little, they're calling it the Somalian plate. And eventually, the Indian Ocean will, as it gets farther and farther away from Africa, the Indian Ocean will flood that area, and maybe a new ocean will form between this Somalian plate and the African plate. I mean, we don't really know if that's exactly what's going to happen, but over millions of years, perhaps that will happen. All right, so this is the general idea. You have these 8 large areas in the lithosphere, and they ride on top of the mantle, and sometimes they crash into each other. The different plates crash into each other. For example, the Pacific plate, or parts of the Pacific plate, are crashing into the North American plate right here. This is where the Rockies are formed. This Nazca plate is crashing into the South American plate, and of course that's where the Andes Mountains are being created. So actually, let me just mention something about that. Remember, we talked about andesitic rock before. And the difference between andesitic rock and just normal granite, right? We talked about the continents are, made of granite, and there's this other similar type of rock called andesitic rock. And really what that has to do with is what's going on right here with this, the Nazca plate crashing into the South American plate. So, there's a lot of sea life. If you think about it, there's lots and lots of sea life. And that all that matter, that dead sea life, is being subducted, because of course, remember, the ocean plate is always more dense than the continental plate. And so as it gets subducted, you have this material that is going beneath the South American plate, but that's building up mountains, and it's made up of slightly different material than let's say in North America, right? Where let's say new granite is being formed. This stuff right here is being formed from ancient marine life that is long since passed away, and that's part of it. That's part of what this andesitic granite, rock is all about. Right? Which again, it's very similar to just normal everyday granite. All right. Anyhow, all right. So these things are all moving around. And so here's another example. Of course, is the Indian plate is crashing into Eurasia, the Eurasian plate right here, and of course this is already land, right? So land and land are crashing into each other. And of course, you get the biggest mountains in the world, right? The Himalayan mountains. What we're about to do is we're going to explore these different boundaries. What happens when the plates crash into each other? When one is continent and continent, if the two continents crash against each other, or if one is part of is deep, way in the ocean, like the Pacific plate or the Nazca plate, and that crashes into a continental plate, or what if the plates just slip past each other? So if one plate is going to the south, like it's happening right here, there's a really famous, in fact, it's called a fault line. So the Pacific plate is going kind of to the northwest here, and the western the western North American plate is going to the south. They're slipping past each other, and that fault is a very famous fault. It's called the San Andreas Fault, right? One of the largest faults. All right. Anyhow, let's look at all that in depth. All right. So the continental plates tend to move slower. Remember what's going on with the continents.